A warm welcome to today's webinar. The webinar is organized by the Indonesian Stainless Steel Development Association and conducted by the International Molybdenum Association and the Nickel Institute. It covers the topic Applications of Nickel-Containing Alloys in Oil and Gas. Today's presenter is Dr. Roger Francis, consultant to the Nickel Institute. I'm your host, Jörg Schweitzer, Manager Market Development in Southeast Asia. With this, I would like to wish you all a very interesting webinar. Over to you, Roger.
Hello, everybody. I think the title of this talk is pretty self-explanatory, so let's get started. So, nickel-containing alloys have been used in the oil and gas industry for over 60 years now. And originally, these were mainly nickel-chromium-molybdenum alloys. But towards the end of the last century, new grades of stainless steel were developed that had good corrosion resistance in oilfield fluids. Since that time, the early alloys continue to be used, and many applications have been found for the newer austenitic and duplex stainless steels, where they offer a lower cost solution. Now, the higher nickel-chromium-molybdenum alloys are still used for particularly demanding applications. And in this talk, I'm going to talk about the corrosion resistance of both groups of alloys with some case histories to show problems and successful applications. So let's start off with the nominal compositions of the stainless steels I'm going to be talking about. And I'm not going to go into this in detail, but basically I'll be mentioning some of the lower alloy austenitic materials like 316L and 904L. And then there are the higher alloy 6 molybdenum alloys, and the three very similar alloys with slightly different compositions. 2205 is a standard 22 chrome duplex, a workhorse alloy in the oil and gas industry. And then for higher strength and more corrosion resistance, there are the super duplex alloys, of which the two most commonly used is Z100 and 2507. Now you can assess the resistance of these stainless steels to localized corrosion, and by that I mean pitting and crevice corrosion, using the pitting resistance equivalent number, or PREN. And this is an empirical formula that relates an alloy's composition to its resistance to localized corrosion. So the higher the PREN, the greater the resistance. Now you may see more than one formula around, but the one I'm using here is taken from ISO 15156 NACE MRO 175, which is the oil and gas industry standard for materials resistant to sulfide stress corrosion cracking. So it's very relevant to this talk today. And you can see that the 6 molybdenum alloys and the super duplex alloys in particular have very high PRENs. So the introduction of AOD melting, which is argon-oxygen decarburization, has led to a range of austenitic and duplex stainless steels with very low carbon content so that they're fully weldable. And the addition of nitrogen improves the strength, the corrosion resistance, the weldability, and also the hot forming characteristics. And the lower nickel and molybdenum content of duplex alloys means that they are lower cost than austenitic alloys of similar corrosion resistance. So now I'm not going to cover a huge range of nickel alloys. I'm just going to talk about the ones that are commonly used in the oil and gas industry. And this has basically been divided into two, where the first three alloys here are used in the solution anneal condition. These are higher nickel, moderately high chrome, and also lots of molybdenum for extra corrosion resistance. And some of them have other alloying additions such as niobium, titanium, or tungsten. But you can see from the PREN numbers that some of these alloys are extremely high PREN numbers. So these are for more corrosion resistant environments. And the corrosion resistance increases with chromium molybdenum content, just as for stainless steels. And tungsten also increases the strength and acts in a similar way to molybdenum in increasing corrosion resistance. Now, what I haven't mentioned is these three alloys here. These 718 is a high strength nickel alloy, and the high strength is obtained by aging. It's widely used in the oil and gas industry. It's been around a long time and it's still used extensively. 925 is the age-hardening version of alloy 825. Similar composition, but it can be heat-treated to get higher strength. And 725 is the age-hardening version of 625. And this alloy has found lots of applications in the oil and gas industry. So despite their high cost, these alloys have applications in oil and gas fluids where conditions are more aggressive or the application is critical. So we also need to talk about mechanical properties, because a lot of these alloys are used on offshore platforms where you're trying to save weight to minimize the amount of steel that's supporting all the activity. So for the austenitic stainless steels, the low alloys are only moderate strength, slightly higher strength for the super austenitic alloys. And usually it's the 0.2% proof stress that's important. Duplex, standard duplex stainless steel, you can see that it's about twice the strength of 904L, about 3 times the strength of 316L. And the super duplex alloys are even stronger. So these alloys, all these stainless steels, are usually used in the solution anneal condition. And it can be seen because of this high strength of the duplex stainless steels. This is also reflected by higher design stresses in standards. And ASME B313 is a standard for piping. And the design stresses for the duplex alloys are much higher than the austenitic ones. So this higher strength means you've got scope for reduced wall thickness and reduced cost, particularly for high temperature and high pressure applications. Plus, this reduced wall thickness can also mean that you've got lower welding costs because of the less amount of filler required. So now for the mechanical properties of the nickel alloys. And you can see that these solution annealed alloys have moderate strength, whereas the high strength alloys, I've quoted some typical values here, but depending on the aging treatment that you can give the alloy, the mechanical properties may be lower, they may be higher. If they go higher than these values, then the elongation is a reflection of the ductility, and this ductility will decrease. So the solution annealed alloys have moderate strength, and you can get very high strengths, and typically required in downhole high pressure wells. If you're using aged alloys in sour brines, it's important that the heat treatment complies with the current requirements of ISO 15156 and ASME 175. And let me give you an example. Alloy 718, besides being used in the oil and gas industry, it's also used in the aerospace industry. The heat treatment that is used for the aerospace industry would not pass the requirements of ISO 15156. So now let's talk about the limits of use of these alloys. Now, austenitic stainless steels maintain their metallurgical stability to over 600 degrees centigrade. Alloy 316L and other 300 series alloys can suffer from chloride stress corrosion cracking at temperatures greater than 60 degrees C in aerated solutions. So this means that hot pipes may crack from the outside if water splashes or condenses on the outside and the chlorides concentrate as the water evaporates. And this can also happen under insulation if it is not properly selected and applied. Now, you can also get this effect with the 6-molybdenum alloys, but only at pipe wall temperatures of above about 175 centigrade. So for a lot of applications, external SCC of 6% molybdenum alloys is not an issue. If we talk about the duplex stainless steels, they're limited to a maximum design temperature of about 270 degrees centigrade, because at temperatures above 300 degrees centigrade, alpha prime phase will precipitate. Now, alpha prime has little effect on the corrosion resistance, but it greatly reduces ductility, and this can result in cracking if the item is then subjected to a shock load. And duplex stainless steels have good toughness at low temperatures, and they're routinely tested at -50 degrees centigrade. With special processing, duplex stainless steels can retain good toughness down to -70 degrees centigrade, and they have been used on a number of projects with blowdown temperatures well below -50 degrees centigrade. with great success. Now let's talk about the nickel-chromium-molybdenum alloys. And again, they're also very stable metallurgically to high temperatures. Now, because the high-strength alloys could further age at high temperatures, their use is limited to a maximum of about 300 degrees centigrade. However, when used in very sour environments, the high-strength alloys have temperature limits that vary with the H2S content. This is all documented in ISO 15156. These are also linked to maximum hardness values, which means it's important to get the heat treatment right. So I'm going to talk now about some applications, and I've divided this up into a number of areas. I'm going to start off talking about materials in sweet brines, and then I'll say something about sour brines. Then I'll say something about injection fluids, and then we're going to talk about downhole applications, subsea applications, of which there are an awful lot out there in the world. And finally, one or two other miscellaneous applications of CRAs that didn't fit into any of those previous categories. So let's talk about sweet brines. So a sweet brine is basically water containing chloride of a whole range of concentrations and a lot of CO2, but no H2S. And all stainless steels have good resistance to corrosion in sweet brines, although there are environmental limits. Alloy 316 is satisfactory up to 60 degrees centigrade, as discussed earlier, but it can be used in sweet brines in the absence of oxygen, which is usually the case in oilfield applications. And again, you can then use it to higher temperatures. Now, to avoid the problems of external stress corrosion cracking and to reduce costs, carbon steel vessels have been lined with 316L, either by weld overlay or wallpapering with thin sheet. This diagram shows the limits of use of alloy 316 in sweet brines, which is taken from the Nickel Institute publication number there, which I'll mention again at the end of the talk. This chart shows the limits of use for 316L in sweet brines as a function of the carbon dioxide partial pressure, the sodium chloride concentration, and the temperature. And you can see that the limits are quite low at high chloride concentrations and high CO2 pressures. But as these decrease, 316L can be used at quite high temperatures and has been successfully used there. At higher CO2 pressures and/or chloride concentrations, it may be necessary to consider a higher alloy stainless steel. Now, one option, if you're making pipe, is to insert a thin 316L pipe into a carbon steel carrier and mechanically or hydraulically expand the pipe to create a good mechanical bond. Now, this picture shows the outer carbon steel carrier, and this thinner stainless steel inner, which is then hydraulically or mechanically expanded. So the stainless steel undergoes plastic deformation, but the carbon steel only undergoes elastic deformation, so that you get a good bond at this interface and it is not going to move about. And this picture shows a liner inside the carbon steel carrier, so you can see how it all works. Now, the ends of the pipe may be clad internally or they may be seal welded so that the carbon steel does not see any of the sweet brine, which can cause huge corrosion of carbon steel. And such pipe as this has been widely used in Asia. So all duplex stainless steels will resist CO2 corrosion up to high temperatures. The lean duplex alloys would be very cost effective. I haven't shown them on my earlier slide, but the lean duplex alloys have less molybdenum and nickel than 2205. They are a similar price to 316L or even lower cost. But the trouble is they're not readily available as pipes, fittings, and flanges. They tend to be used for vessels. So 2205 has been the workhorse CRA in more corrosive brines, sweet brines, and its limits of use, as you can see from this diagram, are very wide. Even at high chloride and high CO2 concentrations, its temperature limit's about 200 degrees centigrade, and it rises as the chloride and the CO2 pressure decrease. Now, super duplex stainless steel is sometimes used in sweet brines at very high temperatures and pressures because its high strength permits wall thickness savings and consequent weight savings. Super duplex has been tested in a brine with 180,000 milligrams per litre chloride and 200 bar of carbon dioxide at 260 degrees centigrade with no significant corrosion. It has been used as wireline in some very hot and high pressure wells in Asia with great success. So now let's move on to sour brines. And sour brines are similar to sweet brines, but there is also hydrogen sulfide. And the hydrogen sulfide concentration determines whether it's going to suffer sulfide stress corrosion cracking. And this is the big risk. You have to remember that hydrogen sulfide is more poisonous than cyanide. If you get a crack and it leaks, it can kill people. So the standard ISO 15156 Part 3 lists the CRAs and their limits of use for particular applications and also for general applications. Now, it's well known that the limits of use are determined by the H2S partial pressure, the chloride concentration, the in situ pH, and the temperature. But ISO 15156 does not always reflect the latest data. But even if there is good data outside the limit in ISO 15156, it doesn't mean you cannot use it. Use outside the limits is permitted, provided adequate test data shows the proposed alloy resists cracking under service conditions. And the final decision is with the end user. Now, alloy 316 is okay up to about 1 bar of H2S and up to 60 degrees centigrade. At higher temperatures, the permitted H2S and chloride concentration drops sharply, and the pH, the minimum pH increases. And so although there are a few uses for 316 at these higher temperatures, frequently higher alloy stainless steels are required. Now, alloy 904L is higher alloy than 316L, but it has not been tested much in sour service, and ISO 15156 limits its use to the same as 316L. Now, based on its composition, it should be possible to use it to much higher H2S limits, but you've got to conduct the appropriate testing before you can do that. Now, 6% molybdenum alloys are more resistant to H2S than 316L, but their maximum H2S concentration also decreases sharply with increasing temperature and chloride concentration. And because of their higher cost and lower strength compared with the duplex stainless steels, there are few uses for the 6% molybdenum alloys in sour service. But there are a few issues where their high ductility in thin sections is sometimes been an advantage. Now, the duplex stainless steels are most susceptible to sulfide stress corrosion cracking in the temperature range 80 to 100 degrees centigrade. And at higher and lower temperatures, their resistance increases. So this means that all the limits of use and the test data are conducted in this temperature range, and a typical temperature for testing would be 90 degrees centigrade. ISO 15156 limits solution annealed 2205 duplex to an H2S partial pressure of 0.1 bar, which is 10 kilopascals. With no restrictions on chloride concentration or pH. However, the resistance to sulfide stress corrosion cracking increases with pH and decreases with increasing chloride concentration. So this graph was compiled from data from a number of reputable laboratories, and it clearly shows that 2205 can tolerate much more H2S than the ISO limit, as shown by this vertical dashed line. So the blue line is at pH, in situ pH of 3.5, and the red line is in situ pH of 4.5. And you can see that at lower chloride concentrations, there's a significant increase in the H2S partial pressure. And if you go to pH 4.5, it's an order of magnitude higher. This has been used by some projects to justify the use of 2205 instead of super duplex or other high alloy materials. So it's something to bear in mind that 22 chrome can be used much more widely than you would suspect just from reading the ISO standard. ISO 15156 limits solution annealed super duplex stainless steels to an H2S partial pressure of 0.2 bar, that's 20 kilopascals. Again, no restrictions on chloride or pH. However, as for 2205, the resistance to sulfide stress cracking goes up as the pH goes up and the chloride goes down. So we've got the same kind of curves we had before, taken from a whole range of laboratories. And you can see that here's the ISO limit at 20 kPa. And even at pH 3.5 in situ, there's an increase at quite moderate chloride concentrations of an order of magnitude, and even more if you go to higher pHs. This is 4.5 and the green line is pH 5.5. These are in situ pHs. Now, this has been used by some projects to justify the use of super duplex instead of nickel alloys. And I'll give you one example, which was the Harold West project in the North Sea, where the H2S was 0.25 bar, which is 25 kilopascals, which exceeds this dashed line. The in situ pH was 4.3 with 120,000 milligrams per litre chloride. So we're sitting somewhere about here with the pH limit. The limit for the pH is somewhere up here. So it's well within its operations. And super duplex has worked extremely well in that project. Now, duplex and super duplex stainless steels have been used extensively for topside process systems because of their high strength and good corrosion resistance. Now, in addition to piping and valves, duplexes have been used for risers, umbilicals, and manifolds. This shows riser. These are super duplex in the carrier pipe being installed on an offshore platform. And this shows offshore manifolds, and these have been made by hot isostatic pressing. And duplex and super duplex manifolds have been made by HIP because it reduces the manufacturing and fabrication costs. If you look, there's a weld around this junction here, and all of that section from there to the end was made in a single piece by hot isostatic pressing. So that after it's been manufactured, it needs to be pickled to clean it. And then the only machining involved is the machining of these flange face connections to the piping. And the only weld is a single girth weld to the next section. That saved all the welding that would be involved in joining T's together, putting welding on an end cap and welding in a put piece between the flanges and the pipe. So that's saved an awful lot of money with hot isostatic pressing. And there are many HIP manifolds in service around the world. Nickel-chromium-molybdenum alloys have very high resistance to sulfide stress corrosion cracking. And there are no restrictions on the use of alloys 825 and 625, or C276 for that matter, in the solution anneal form. The high-strength alloys have limits on H2S, and these limits decrease as the temperature increases, and there's also a maximum hardness. Even with these restrictions, these alloys are very resistant to sulfide stress corrosion cracking, and much more so than the stainless steels. They may be used for smaller components in equipment such as valves, although they can be used for larger items and very aggressive fluids. More commonly, they're used as weld overlay on items such as valves. Now, alloy 625 is the most commonly used as a weld overlay, either on carbon steel or a low alloy stainless steel. Alloy 825 is not suitable for a weld overlay because the dendritic microstructure of the weld greatly reduces its corrosion resistance. This photo shows 625 weld overlay on a carbon steel ball from a large ball valve. and such weld overlays have performed very well in service. Where larger diameter nickel alloy piping is required, it's possible to reduce costs by using a thin alloy 625 or 825 pipe and expanding it into a carbon steel pipe, as I showed earlier for 316L. Provided care is taken when butt welding the pipes to avoid excessive dilution, these pipes work very well. There are numerous examples of such pipe in aggressive produced fluids. Now, when the produced fluids are very hot and aggressive, it may be necessary to cool them to reduce the aggressivity and enable further transmission in carbon steel or low alloy stainless steel pipe. This heat exchanger is cooling process fluids on an offshore platform. This shows it in fabrication. The tubing is C276 because it would resist the aggressive process fluids on the outside, and it would also resist the seawater on the inside. The water box here carrying the seawater was made from carbon steel clad with alloy 625. And the tubes were operating at about 80 degrees centigrade and the water box at about 65 degrees C. And this unit performed very well in service. So now I'm going to move on to talk about injection systems. Now, to maintain well pressure and increase production, it's common to inject water around the producing strata at high pressure to basically make the well more productive. The typical method is to inject the produced water where there is sufficient. So you've stripped out the oil and gas, this will usually have significant chloride concentration, and there'll probably be traced some small amounts of CO2 and possibly H2S, but it will be deaerated. Now, if there's insufficient produced water, then seawater is deaerated and injected instead. And depending on the quality of the water treatment, the dissolved oxygen may be anything from 20 to 100 parts per billion. And this can have a significant effect on corrosion. This is a typical injection pump, and here's the injection pump in the middle here. And these have to deliver anything from 100 to 400 bars. So these are multi-stage pumps, and you can see all the associated equipment, the motor, gearbox, and all the ancillary control equipment. It's quite a big skid, but the pump is this bit here, and these are the suction and discharge flanges. Now, because of the high pressures and the need to reduce weight for the injection pumps, super duplex is the most commonly used material. Because thinner walls saving weight compared with using 2205 duplex. And super duplex injection pumps have a very good track record in the offshore oil and gas industry. Now, sometimes it's necessary to supplement the produced water with deaerated seawater. And if the deaeration is not adequate, there's a risk of crevice corrosion. So this table shows the effect of dissolved oxygen content in ppb on the crevice corrosion resistance of a super duplex stainless steel in a high chloride brine. And the high chlorides was about 100,000 milligrams per litre. And there was also 1 bar of CO2 to represent the fact that some CO2 has not been stripped out from the produced water. And what you can see here is that raw super duplex and welded super duplex showed no localized corrosion whatsoever. P's pass. F's fail, even at high temperatures, and up to 410 ppb of oxygen. The problem was with the cast material, and cast material was okay up to 120 with 50 ppb, and even up to 100 C with 200 ppb, which is 200 ppb is not common. As I said, 50 is a typical value, and some platforms with good water treatment can get it down as low as 20. Now, at 120 C, you've exceeded all current applications. To the best of my knowledge, the maximum injection temperature currently is about 70-75 degrees C. So we're well away from any limits. So, which is why super duplex performs well. And tests, I haven't shown the data, but with 2205 duplex with 50 ppb of oxygen, it was only satisfactory up to about 60 degrees centigrade. Now, if you've got H2S in the produced water, it will react with any dissolved oxygen to produce a small amount of elemental sulfur. The H2S concentration will be in the ppm level, so it will exceed that of the oxygen, so it will remove all the oxygen. So the water will now be oxygen free because the H2S concentration, as I said, is very high. And at temperatures up to about 100 degrees centigrade, cast super duplex will still be satisfactory for the injection pumps, even with the presence of some elemental sulfur. Now, if there are strontium or barium salts in the produced water, then the injection water must be low in sulfate ions. Otherwise, you'll produce, when you inject water to boost performance, you'll form insoluble barium and strontium sulfate. This will block up the pores in the oil producing strata, and you'll reduce production rather than increase it. So to prevent this, the injection water must first be passed through a sulfate removal package. And this is very similar to a seawater reverse osmosis desalination unit, but with special membranes to remove the sulfite. And this shows a typical sulfate removal package. This is going to a platform off the Brazilian coast. These are the FRP membrane cells, and all the piping around it is super duplex, because we're talking about pressures of seawater here of 60 to 100 bar, and it's aerated seawater. So this will, all the active pipe work is super duplex stainless steel. And this photograph shows a typical module being installed, a different module to this one, but being installed in a platform in the North Sea. Now let's talk about subsea. And this is just a schematic diagram of a typical wellhead, but they can be very variable with all sorts of valves and piping, depending on exactly what the well requirements are. But this shows all the different construction with all the pipes within pipes, including the casing and the production piping, and the hangers, etc. So the wetted portions inside that see the well fluids, any alloy that you use must resist those. If the alloy is used externally, then because we're talking about subsea wellheads, it must resist seawater. Now, there's usually a significant amount of carbon steel used in the wellheads, and the external surfaces are usually coated, and they also have cathodic protection. So this means that any CRA in contact with the seawater must resist hydrogen embrittlement. On the produced fluid side, nickel alloys are commonly used for hangers, chokes, and other downhole equipment. And as it's important to keep the size down, the high-strength nickel alloys such as 718 are routinely used. Now, austenitic stainless steels are resistant to hydrogen embrittlement, which is also known as hydrogen-induced stress cracking, or HISC. It's the same thing. But duplex stainless steels are not resistant. And there have been a few failures of duplex associated with very high stresses and undesirable microstructures. And this shows an undesirable microstructure. The darker phase here is the ferrite. These light stringers are the austenite, and it's roughly 50-50, typical for a duplex stainless steel. But ideally, the austenite stringers should be parallel to the external surface, because they're austenitic, they will block the cracks, instead of which a crack has developed here. And because the ferrite is running at right angles to the surface, the crack can propagate freely down the ferrite without restriction. And in this particular instance, when the system was pressure tested, it leaked because of the hydrogen cracking. Now, the other thing is you need stresses exceeding 90% of the 0.2% proof stress to get hydrogen embrittlement in duplex stainless steels. Now, the EMUA, which is a UK organisation, which is the Engineering Equipment and Manufacturing Users Association, have produced guidelines to avoid hydrogen embrittlement of duplex stainless steel. So these are very practical things that can be done so that when you can safely use duplex stainless steels without getting hydrogen embrittlement. And DMV have produced design guidelines also to avoid hydrogen embrittlement. And since the publication of these two documents, hydrogen embrittlement failures are rare. Now, the high-strength nickel alloys can suffer hydrogen embrittlement if used subsea and exposed to CP under certain conditions. And they can also suffer hydrogen embrittlement if they're used downhole and coupled to a large area of carbon steel, such as a carbon steel casing. Such failures are rare, but they have occurred. A number of proprietary nickel-chromium-molybdenum alloys have been produced that offer similar strength to alloy 718, but greater resistance to hydrogen embrittlement. But there's been limited use of these alloys to date, so I can't comment on how effective they are. Now, when the produced fluids are very hot and the wellhead is several kilometers from the platform, it would be very expensive to use a long CRA platform. In some cases, the fluids are cooled to reduce the temperature and pressure so that the pipeline can be in carbon steel. And this shows such a subsea heat exchanger. The piping is super duplex stainless steel. Here we can see, and the pipes zigzag up and down this frame, which is made of carbon steel. It has a high quality coating on it, and it's further protected by zinc anodes. So it's cathodically protected. And this means that the stainless steel is also seeing cathodic protection, and so hydrogen embrittlement is a potential risk. So the welding was controlled to minimize residual stresses, and the unit was located subsea in the Far East, from my perspective. A tsunami occurred close to the heat exchanger a year or two after insulation. But on subsequent inspection, nothing had moved and there was no cracking. So this was a robust installation, which was not suffering hydrogen embrittlement, and there have been other such installations. Let's just talk about one or two other applications of CRAs. So if you're unloading an FPSO to a tanker, you're taking the oil on board and any impurities it's got, which is water, maybe a bit of CO2. And this is a typical swivel joint connector. These are made from cast super duplex stainless steel, and each of these sections can rotate against the next one. So it has to resist seawater on the outside and oil with impurities on the inside. And because you want to keep the weight down, cast super duplex stainless steel combines all the necessary properties. Now, because of the high pressures between these swivel sections, there's a risk of galling. And so they were coated with a cobalt chrome alloy applied by high velocity oxyfuel process, which gives you a 99.9% dense coating. And that worked extremely well in service with no galling whatsoever, and no corrosion either. Now, super duplex has also been used for anchoring straps on buoyancy floats fitted to risers. So here's the buoyancy devices. Here's the holder with a strap, and all the metal clamps, they're super duplex because it resists seawater. Similarly, the two buoyancy devices are bolted together with super duplex bolting, and that's a wide use of super duplex stainless steel on risers. Now, a North Sea platform needed to cool hot gas coming to the platform at about 100 bar and 200 degrees centigrade. Super duplex was chosen for this heat exchanger because of its high strength and its resistance to both the gas and the seawater. But because of the high pressure, the gas was on the tube side. So this is the inlet box, and then this is the heat exchanger. So the seawater's on the shell side, and the high pressure gas is on the inside of the tubes. All the shell side components were super duplex to resist seawater corrosion. And to avoid any corrosion at the tube sheet joints, where you might get crevices, the tubes were back face welded to the tube sheet, where you machine a little nipple on the face of the tube sheet for each tube, and internally weld it to the stub with a special torch. This heat exchanger performed well in service. Now, another subsea application required activating pistons, which could see both seawater and aggressive produced fluids. So these are made again of super duplex stainless steel. Because these are pistons, they're highly polished so that they create a good seal. And these worked extremely well. So now I'm going to talk about topsides offshore, because offshore platforms, the atmosphere there is very aggressive because of the high chlorides and the possibility of splashing, and in many cases, higher temperatures. So ISO 9223 categorizes atmospheres for corrosivity, and topside offshore is often C5 class, which is aggressive, or CX, which is very aggressive. Basically, it means it's off the scale. Now, carbon steel with a coating is often used offside, but the coating generally has a limited life and needs regular inspection and repair. Now, stainless steel offers a zero maintenance option for topside. It doesn't need painting and it can resist corrosion, but it's important to select the correct grade of stainless steel according to the atmospheric severity. Now, these slides show some panels which were exposed for 5 years on the coast at Brest in northeastern France. So the atmosphere here is categorized as C5. And here we've got 316L, which has shown some staining, but nothing too severe. These are two lean duplex alloys, and these show more staining and some pitting. And then there is no corrosion whatsoever on the 2205 duplex. So in this sort of C5, 316L is passable. If you don't want any corrosion whatsoever for any reason, then 2205 is a better choice. Now, some stainless steel panels were also exposed for 4 years at a coastal site in Dubai, where the conditions were CX. And this is very close to the sea, very aggressive. And what you can see here is that 2205 here was better than 316L. Unfortunately, I couldn't find the photograph for it, but these are two lean duplex alloys. You can see there's a lot of corrosion here, and where the crevice has been, there's been a lot of crevice corrosion of lean duplex alloys, and it was very similar for 316L. There's less staining and shallow pitting here on 2205, but there's still crevice corrosion on this aggressive atmosphere, and only super duplex stainless steel showed minimum corrosion here in the bulk area and no crevice corrosion whatsoever. So in really aggressive situations, 2205 is going to be a minimum, and if you really need no corrosion at all, then super duplex is a better choice. Stainless steels can be economically used offshore for module walls, conduit and cable trays, but it's important to select the correct grade for the atmospheric conditions. Alloy 316L is routinely used for cable trays and instrumentation tubing and fittings for pressure gauges, etc. So this shows some typical stainless steel trays for cables, and this shows typical instrumentation tubing and couplings widely used in all sorts of places. Now, where the tubing's exposed to aggressive offshore atmospheres, failures have been seen, typically due to crevice corrosion under clamps and mounts on some like 316L instrumentation tube, because seawater gets into those crevices and then creates corrosion, and eventually you get a leak. In these cases, it's been necessary to upgrade to 2205 duplex or even super duplex in severe cases. So let's wrap up this talk with a few conclusions. There's a range of stainless steels and nickel alloys that have good corrosion resistance in oil and gas fluids. The atmosphere on offshore platforms is very aggressive, and stainless steels can offer a cost-effective solution with zero maintenance and long life, but it is important to select the correct grade. The limits of use of the duplex stainless steels in sour service are much higher than is allowed in ISO 15156, and by taking advantage of this, you can avoid using more expensive alloys. And stainless steels and high nickel alloys may be used as weld overlay or mechanically bonded cladding on carbon steel for larger components and piping to reduce costs. Now, a few words about some further information. The International Molybdenum Association produces 2 booklets on practical guidelines for fabrication of stainless steels. This one here is for the practical guidelines of austenitic stainless steels, and this was updated fairly recently. The associated one for fabricating duplex stainless steels was issued in 2014. Now this document has been updated, and I'm hoping that the new edition will come out later this year. And finally, the Nickel Institute publication 10073 discusses corrosion-resistant alloys in the oil and gas industry and gives some hints at where they can and can't be used. This was written by Bruce Craig and Leanne Smith, both of whom have many, many years of experience in the oil and gas industry. The one drawback to this publication is it does not discuss super duplex stainless steels, and which is a drawback. Apart from that, it's very good. So thank you.
Thank you very much, Roger, for your excellent presentation. Dear listeners, if you have any question concerning this presentation or about any nickel-related topic, kindly send us your question via our webpage. Once you enter www.nickelinstitute.org, you will immediately see the yellow banner Technical Help. Click on it, register, it's free of charge, and fill in your question. One of our experts will come back to you fastest. Thank you all for attending this webinar. We are looking forward to have you on one of our next webinars again. Goodbye.